Okay, complex motion. We're going to be dealing with two basic types of motion and the graphs and solving problems with them. The first type of motion is going to be a two-stage motion problem. That's going to be a situation where we deal with multiple periods of time that have different accelerations, and then we're going to deal with chase problems, and that's a problem where one object is catching up to another object or something like that. In a two-stage motion problem, we've talked about throughout these videos how, at least within the scope of this course, we can't handle a changing acceleration. The acceleration has to be constant for the whole time period for us to use the things we've been doing. That's not entirely true. If there are regions of constant acceleration, like if the acceleration is one thing for a while and then it's something else for another time, we can handle that as well. And that's what this video is going to look at. With if we look at this situation here, car accelerates from rest at 4.2 meters per second squared for 4 seconds. We can view that as our first stage. And then if it has to brake to rest over the next 6 seconds, that's a second stage. If we treat those two stages separately, then we can still use our tools that we have for constant acceleration. We just have to treat each stage as if they're unrelated to each other. So to do this, I'm going to draw an axis here, get us going. I'm going to start with the velocity time graph. The velocity time graph is often easier. And it's going to go, let's say that's up to 4 seconds. That'll be until that's when the car reaches its maximum speed, and then it says it brakes over the next 6 seconds, which to me means that it's at 10 seconds when it finally comes to rest. So those are the two critical or important times in our motion. It says it starts from rest, and it says it ends at rest. And we know that it has a uniform acceleration in the first part, so it's going up. And in the second section, it has a uniform acceleration coming back down, so it goes something like that. But before we can do much more with this graph, we really need this value right here. If I just look at this stage 1 problem, then for stage 1, I know I have an acceleration of v1 of 0, an acceleration of 4.2 meters per second squared. There's no direction given, so we can say positive x or something like that, but it's not important. If it doesn't say, we can just work with it and sort of ignore the direction situation. It's the final velocity we're looking for, specifically after a time of 4 seconds. So a few videos ago, we did a equals v2 minus v1 over t, which means 4.2 meters per second squared equals v2 minus 0 over a time of 4 seconds. And if we multiply both sides by 4, then we can get a v2 of 16.8 meters per second. So that gets us that maximum velocity value. And that's a pretty useful little graph, and that should help us to be able to create our position time graph. Again, the critical times for these two graphs are going to be the same, right? It's accelerating up to 4 seconds and then slowing down until 10 seconds. I'm going to look at each stage separately. So in stage 1, then I'm going to say it's accelerating in a positive acceleration, which means we're looking at a quadratic that opens up. Now it's starting from rest and it's speeding up, so it's this part of the quadratic right here that we're going to observe. So I'm going to put that on in red, and then I'll sort of refer to this stage as red here. So I'm going to goes up like that. It's sort of curving up to some maximum speed. I guess the slope at this point would be exactly 16.8. That corresponds to here. So we can use the area of that red shaded region to come up with what this displacement would be at this point. Has a base, the triangle is a base of 4 and a height of 16.8. So if I use the formula for the area of a triangle, base times height divided by 2, that means 4 times 16.8 divided by 2. This works out from units to meters per second and seconds. 16.8 times, I get 33.6 meters. So that would be 33.6 meters. I'm going to look at the second stage in green. That's this guy right here. Here we can see we have a negative acceleration. So we're dealing with a concave down parabola. And here we're starting with some initial fast speed and we're going to 0, or the vertex has to occur at 10 seconds. So we're going to deal with that shape of parabola right there. It's going to start here and come up to the flat spot. We need the area of that shaded region as well. This time the base isn't quite as obvious. It's 6 and we have a height of 16. So here I'll call it A2. Base times height divided by 2 gets us 6 seconds times 16.8 meters per second divided by 2. And we get 50.4 meters. Now we have to be a little bit careful here. That's the displacement, that's not the position. What that means is that in this section here, it's gone additional 50.4 meters. Doesn't mean that this value is 50.4. This value right here would be the sum of these two displacements. You have two different times that you did two different displacements over. So if you did 33.6 plus 50.4, you would get a total of 64 meters. And that's what this value, try that again. That's what this value would be. I'm going to try that addition again too, because that'd be 84. Sorry, that'd be 84 meters. Okay, so that's a pretty detailed position time graph and displacement time graph. I guess just I don't want to lose marks on something silly, so I'll make sure I put that that's in meters. And other than that, I think I'm okay.